who will tell us about the D-critical locus structure for the Hilbert N of omega S.
Oh, thank you so much for the introduction, and thank you for inviting me for this great conference, and it's my pleasure to speak here. So I will start with my talk. So this will be on D-critical local structure for Hilbert scheme of zero-dimensional subschemes on some local Calabi-Yau threefold. Oh, by the way, can you hear me well?
Yes.
Okay, thank you.
Yes.
Okay, so this is joint work in progress. With Sheldon Katz. Okay, so D-critical local structure. This is an ingredient in the definition of Motivic Donaldson-Thomas invariant. So in this talk, in the first part, I will give a brief introduction to Motivic Donaldson-Thomas theory. And then the second part will be a discussion on work in progress on constructing D-critical local structure. For Hilbert scheme of zero-dimensional subschemes or length n subschemes on some local Calabi-Yau threefold, where X is the is local P2 or Fn, meaning that is the total space of canonical bundle on P2 or Fn. Okay, so the first part will be like a brief introduction to Motivic Donaldson-Thomas theory. Although later on the target space X will be some local Calabi-Yau, but for the first part, just to simplify explanations, I will assume X to be a compact Calabi-Yau threefold over C. So for the first part,
could you say again what Fn was?
Oh, this is the projective bundle over P1 of O direct sum O1.
Thank you.
Yeah, sure. Thank you for the question. So let me start with the first part of the Motivic. This is a very brief and sketchy introduction to Motivic Donaldson-Thomas theory. Okay. Yeah. So I will use X as to denote the target space and use M to denote the moduli space. Again, to simplify explanation, in the first part, I will assume X to be a compact Calabi-Yau threefold. So this is a compact Calabi-Yau threefold over C. And later on, we'll work with local Calabi-Yaus because we work with zero-dimensional subschemes. So this always shift with compact support. So there's no problem. It doesn't cause a problem for the theory, but just to simplify explanation. Right, and all the schemes show up in the talk will be like very reasonable schemes, so it's separable and locally of finite type. Okay, so before the introduction to Motivic Donaldson-Thomas theory, let me just quickly review what Donaldson-Thomas theory is. This is sorry. So Donaldson-Thomas theory is an enumerative theory. So roughly speaking, it counts curves on Calabi-Yau threefold. So the precise definition is that the moduli space parameterize the G-Ziegler stable coherent sheaf on X, with a fixed topological invariant, chain character 1, 0 minus beta minus n. This is in the rational cohomology of X. With a trivial determinant, or precisely with a trivialization of the determinant. So one can see that any such sheaf is torsion-free, embedded into its reflexive hull, and this reflexive sheaf is rank 1 with a trivialization of determinant, so it can only be the structure sheaf of X. So any such sheaf is actually an ideal sheaf of a subscheme of some subscheme C in X. So C is supported in dimension 1 with the corresponding chain character. Okay, so this is like a point-wise analysis, but actually one can show that this moduli space is isomorphic to Hilbert scheme with the corresponding chain character. So the later one may be a more familiar space to people. So from the point of subscheme, the viewpoint of subschemes instead of moduli of sheaves, the objects in the moduli space will be pure curves, or pure curves with some 3 points, pure curve with some 3 points, with some embedded point, or some curve with some thickening. And also like with embedded point with 3 points. So it's like one-dimensional subschemes. This is from the viewpoint of categorification of moduli of curves. Okay, so although the moduli space are isomorphic, so the DT moduli space are isomorphic to Hilbert's scheme. So, but if you realize the moduli problem, if you realize the space as a solution of moduli of sheaves instead of moduli of subschemes, then the deformation abstraction theory is much nicer. So there is this is a result by Thomas. So there exists a perfect abstraction theory. On MDT or associated to the moduli of sheaf problem. So this is a two-term complex in the bounded derived category of coherent sheaves, quasi-isomorphic to a two-term complex in the bounded derived category of coherent sheaves with some extra properties with a map to the cotangent complex such that it induces isomorphism on H0 and epimorphism on H-1. But I don't want to give too much detail of this. But the point is that then one can use the technique of Li Tian or Baron Fantecchi to use this perfect abstraction theory to construct a virtual cycle in shell. This is so-called a virtual fundamental class. So when we are on the case when X is a Calabi-Yau threefold, and in this case the deformation of the sheaf is controlled by X1, and the abstraction space is X2. So the deformation and the abstraction are actually due to each other, and these two bundles are of the same rank. So in this case, this virtual fundamental class is actually lives in child 0. And then the Donaldson-Thomas invariant is defined to be the degree of the virtual fundamental class. And this is integer. So in the really nice case, this virtual fundamental class like correspond to the locus where a general section of abstraction bundle vanish. So it's really like the counting is like counting some objects satisfying some nice deformation property. But it's like a whole, it's a relatively complicated story. So let me just say that the invariant is defined by the deformation abstraction theory, and is actually the degree of the virtual fundamental class constructed here. So the example would be when the moduli space is smooth. Then the perfect abstraction theory is given by this, the tangent bundle to the cotangent bundle with the zero map. And in this case, the DT invariant is actually the top chain class of the cotangent bundle, and it's signed Euler characteristic of the moduli space. So this gives a different way to view this invariant. This invariant is defined by deformation abstraction theory, and but in the nice case, for example, when the moduli space is smooth, it's actually equal to some topological invariant associated to the moduli space itself, which is the Euler characteristic of the moduli space. And it turns out that this viewpoint that the DT is actually the Euler characteristic of something is more generally true. So this is a deep result by Aaron. So actually, so here X is Calabi-Yau threefold. Then the DT invariant is actually a weighted Euler characteristic. On the moduli space, and this weighting is induced by a constructible function on MDT. Okay, so this is called invariant function. Right, so this says that this viewpoint of the DT invariant equals to the Euler characteristic of moduli space is like more generally true, and it motivates that there may be a much richer structure behind the Donaldson-Thomas invariant. So there may be some constructible structure lives on the moduli space, lives on MDT, such that this DT invariant is actually an invariant associated to that structure, which is by taking Euler characteristic of that structure. And in the really nice case, when the moduli space is smooth, then this constructible structure is just the class of the moduli space itself. So when you take the Euler characteristic of the moduli space, I mean the signed Euler characteristic, you'll get the DT invariant. So this like motivates there could be a categorification of this invariant. It could be a Motivic class, it could be some perverse sheaf, but it's some constructible structure lives on the moduli space. Okay. So let me say a few more about this invariant function. So this function is in general very difficult to compute, but in a special case, when the moduli space is globally a degeneracy locus, so it's the zero locus of df equal to zero locus of df equal to 0, where f is a regular function on a smooth scheme U. In this case, this invariant function evaluated at every point in the moduli space is given by it's a function of the Euler characteristic of Mueller fiber at that point, where P is Mueller fiber at P. So so this like gives more hint of what this constructible structure should be look like. So originally the DT invariant, one can think about it as integrating variant function on the moduli space. Well, in this case, in the special case, when the moduli space is globally a degeneracy locus, the variant function actually is a function of Euler characteristic of the Mueller fiber. So this constructible structure, this gives a hint that this constructible, one way to define this constructible structure is to integrate the actual Mueller fiber or the Motivic incarnation of it, the Motivic Mueller fiber on the moduli space, and obtain a Motivic class, and that could be the definition of Motivic Donaldson-Thomas invariant. So this leads to the definition of Motivic Donaldson-Thomas invariant. Okay, so that's like the motivation part. So this invariant, so now let me like briefly state the definition for Motivic Donaldson-Thomas invariant. So this lives in a monodromic Grothendieck group over some scheme S, and this first defined by Kontsevich Selbelman. And later by Bussy, Joyce, and Meinhardt. Okay. So in this talk, I will mainly follow BJM's definition. Okay. So first, let me explain where the invariant lives. So this mu definition of this mu hat. So let mu n be the nth root of unity. Then there's a map from mu nd to mu n by taking u to power d. So this gives the all roots of unity an inverse system structure. Then this mu hat is given by the inverse limit of mu n. Okay, so this is the group which the goal is to capture the monodromy action of the nearby fiber. So then the monodromy Grothendieck group, so this is called the monodromy Grothendieck group. Okay, so this is a Billion group generated by S schemes together with a mu hat action. So this is a mu hat action. And modeled out by equivariant Caesar relationship. Okay. So denote the A1, the class of A1 in this group by L1, by L. Then the monodromy Grothendieck ring is obtained by formally joining the inverse of L. So there is an obvious product structure on this ring by taking fiber product of two varieties over S and then taking the product of the actions. There is a less obvious product on this ring. This is called the Lu-Yanga's convolution product. Let me skip the definition of this product. But this one is this is the actual product used in the definition of Motivic DT invariant. Okay, so now so this is where the this ring together with this product, this is where the invariant lives. So now let's define the invariant. So the first step is that when the moduli space or any space you are interested in, this is globally a degeneracy locus. Again, this is the f equal to 0 for f, a regular function on a smooth scheme U. in this case, one can associate to this moduli space so-called Motivic vanishing cycle. Again, this definition is pretty long, and I won't directly use it in this talk. So let me just say that so this Motivic vanishing cycle like captures the monodrome information of the nearby fiber. It also remembers the information of this regular function f, and so it's like the space where the class where fulfills the hope of integrating Motivic lunar fiber like on the moduli space. Right. So the point is that when the moduli space is globally a degeneracy locus, then there is a way to associate a Motivic invariant to that space, which satisfy the like people's hope of what this class should satisfy. Okay. But it rarely happens that the space is actually globally the space we are interested in, or the moduli space is globally a degeneracy locus. So the example for this would be like when MDT is smooth, this is trivial case, and also like for hue NC3, or the moduli space of some quiver representations. But it's not this doesn't happen like often that the moduli space is globally a degeneracy locus. So, but luckily, so there are several interesting moduli spaces. They can be covered by degeneracy locus. So this is a theorem by E. Let me check the name. Then so by BVJ that the moduli space of coherent sheaves on a Calabi-Yau threefold. This is locally covered by degeneracy locus. This is just part of the theorem. So the precise notion for this, like the moduli space can be locally covered by degeneracy locus. This is called decritical locus structure. And let me give the precise definition of that here. So first, this is a theorem due to Joyce. Let M be a scheme. Again, it's a very reasonable scheme, so it's locally of finite type. Over C. Then there exists a sheaf as a sheaf of vector space on M. So this sheaf, Joyce sheaf, is uniquely characterized by several properties, and in particular, it has the property that for any Zariski open subset of M, if one can embed this R into some smooth scheme U, then this sheaf restricted to R is given by the kernel of the differential map. So this is the kernel of this map. Let's denote the first map by eta R U. So there exists such a sheaf, and it's for any Zariski open subset, like it is realized as a kernel of the differential map. And then the definition, a decritical locus structure is a pair. It's a scheme, again, locally of finite type, separated, and with a section S in this sheaf. It's actually a section of a direct segment of this sheaf, but let me omit the detail there, such that for any point P in M, there exists a Zariski open neighborhood of P, such that this R can be globally realized as a degenerate locus. So this is the first property, such that this R can be embedded at some in some smooth scheme and realized as df equal to 0. Okay. And furthermore, so this section S remembers the compatibility information of these local sections. So this S restricted to R is actually the I inverse F plus I RU squared. Right. So a D-critical local structure consists of two pieces of information. So it's a scheme which locally can be covered by degeneracy locus, and also there is a section of a global sheaf which records the information of the local sections. The local sections. Right. So now
Quick question.
Sorry, is there a question?
Yeah, when you write I inverse, you really mean just the inverse image is a sheaf. You're not tensoring with the structure sheaf of R. When you write I inverse, so is sheaf inverse image, or you're taking the sheaf inverse image? It's I star, often I star.
It's just a sheaf inverse.
I see. So
yeah.
I is not okay. Great, thank you.
Mm-hmm. Yeah. Right. Thank you. And oh yeah. So yeah. So the picture is as follows. So so now we have the moduli space. Okay, and then it's not globally a degeneracy locus, but it can be locally covered by some degeneracy locus. So this is Ri, Rj. Okay, so this Ri is some zero locus of dfi, and Rj is the zero locus of some dfj in ui and uj. And then so for this local, so because Ri can be globally realized as a degeneracy locus, so then there one can associate Motivic vanishing cycle to this space, MFUJFJ. Right. So now, if these Motivic vanishing cycles they naturally agree on intersections, then one can just glue them together to get a globally well-defined Motivic invariant. But this is not the case. Actually, it's a theorem in PJM saying that if the Ra and R, so if you have Ri embed into Ui as a degeneracy locus of dFi, and then you have Rj embedded into Uj, and then this is dfj, the zero locus of dfj. So when the third order sequencing are isomorphic, then the Motivic vanishing cycles are isomorphic to one another. So the Ui, meaning that the Ui Ri Ui Q isomorphic to Uj mod by Rj Uj Q. When this is true, then the Motivic vanishing cycle would agree. But one can see from the definition of the D-critical of this section, actually it only remembers the sheaf only remembers the information up to the ideal square. So just from the structure of the D-critical locus, it's not enough to guarantee that these locally defined Motivic vanishing cycles naturally agree on intersections. So one need additional piece of information. So that's the third piece of information in the Motivic DT definition, and that is called orientation data. So it turns out that the difference is not too bad. So right. So given a D-critical locus, so given a D-critical locus structure, then there exists so this is the theorem by Joyce. there actually exists a line bundle on M, which is called the virtual canonical bundle. This is associated to the D-critical locus structure. Again, this line bundle is uniquely characterized by several properties, but in particular, it has the property that is restricted to R, where this RU Fi is a chart as before, as in the definition. So this is actually the canonical bundle of U squared restricted to R, where this is just a Euro canonical bundle because U is smooth. Then one can pick a square root of this virtual canonical bundle, assuming there exists a square root of this virtual canonical bundle. Then the difference between this and the canonical bundle of U, this restricted to R. So this is a two torsion element in the group of line bundles. So it's measured by a principal Z2 bundle. Denote the principal Z2 bundle by PR. So this is the principal Z2 bundle. And then one can associate Motivic weights to this principal Z2 bundle by taking R with the trivial action minus the bundle with the mu2 action. This lives in mu hat R. So now, so this is like the fixing term where to fix the incompatibility of the Motivic vanishing cycle. So before we have this locally defined Motivic vanishing cycle, they don't naturally agree on intersection. But if we have a choice of the square root of this virtual canonical bundle, then we can fix the Motivic vanishing cycles by these principal Z2 bundles. And after this fixing term, then there exists naturally this Motivic class. They agree on intersections, and one can glue them together to get a well-defined global invariant. So I didn't write down the def. So the definition of orientation data is a choice of the square root of this virtual canonical bundle. Together with some compatibility condition, it's called the co-cycle condition. Due to conservation supplement. Okay. And then with such a choice, now we collected all the pieces. Then the theorem by BJM is that if you have a D-critical locus structure, so it's a scheme locally covered by degeneracy locus together with a section remembering the local Fs and plus a choice of orientation data, then there exists a unique globally. So there exists a globally well-defined Motivic invariant. I'm not writing it properly, sorry. So there is a globally well-defined Motivic invariant denoted by MS, such that for any critical chart, RU-Fi. So this is R realized as df equals to 0 in EU. This global defined invariant restricted to R is given by the Motivic vanishing cycle times the contribution coming from orientation data. Okay, so this is like the definition for Motivic DT invariant, which is the categorification of the classical DT invariant. Okay, so that's like finished the introductory part. Sorry for a lengthy introduction. So then I will talk about the work on D-critical local structure. So from now on, the target space X will be local. So the total space of canonical bundle on P2 or Fn will be a local Calabi-Yau threefold. So the theorem is that this there exists a decritical local structure. Hilbert omega s, where Hilbert is the Hilbert scheme of length n subschemes on the total space. Okay, so I should mention that induced by Hilbert C3. I will say more about this point later. C3s. I should mention that there exists a canonical decritical local structure on the moduli of sheaves. So this is the theorem by PTVB. So this is due to Cohen. And also like BBVBJ as before. So there exists a canonical decritical local structure. Moduli of sheaves. Calabi-Yau threefold. So the result is that the PTVB showed that there is a -1 shifted symplectic structure on the derived moduli scheme, and then Joyce and so VVJ showed that there is a truncation of that -1 shifted symplectic structure, and the decritical local structure is given by the canonical decritical local structure is given by the truncation of that -1 shifted symplectic structure from derived schemes. But the construction here in this theorem is very explicit. So we don't know the relation between this between the decritical local structure here and the canonical one coming from derived geometry, and that would be an interesting question to know maybe in future work. Right. Let me say a few words on the motivation of studying this decritical local structure. So this is by a result by Barron, Brian, and Sanjoy. So this is after definition of conservative supplement, but before the definition given by BJM, by Bussy, Joyce, and Mainhardt. So in this paper, they give a definition of the absolute motivic class of Hilbert X for X a compact Calabi-Yau threefold. And then they computed the generating series for that. Right. So the goal of studying this is to see like use Joyce definition, write down Joyce definition, and to define the motivic invariant and see that whether using this decritical local structure we can recover the computation given by BBS using their definition of Hilbert X. Right. So then.
Hang on a second. Is it the case that if you had orientation data, then you'd have a well-defined class in this K theory of varieties with an action of mu?
Yes.
Because you have this decritical locus structure?
That's right. So you need a decritical local structure, and then you need a choice of orientation, and that's enough to have a definition of the motivated class.
Do we know there is such a choice of orientation?
Yeah, that's like what I'm trying to write down. Yeah, there is. Right. Thanks.
Okay.
Yeah. So this is
So is the class, sorry, this is just a naive question. Is the class in the K-theory of the varieties what's getting denoted in the bottom with Barron, Bryan, Sandroy with the brackets? With
Yes.
the bracket Hilbert? So that's a corresponding class in this K-theory of varieties?
Yes. So they define this invariantly.
Got it. Okay. All right.
Right. So this is actually this is absolute class of push forward to K, and this is the class with no action actually, and right. And then the computation, like using this decritical local structure here, and then the orientation data I'm going to state, and one can give the, like using Joyce's definition, one can give the definition of a Motivic class which agrees with their definition. Thanks. Okay, so this follows Ben Davidson's work. So the proposition is that so if we let F be the universal object, Hilbert, then and let pi be the projection from Hilbert x cross x to Hilbert x. So F is a sheaf from Hilbert x cross x. Then the virtual canonical bundle in this case, this is isomorphic to the determinant of pi push forward the universal sheaf due squared. So as a result, so this follows the work of Ben Davidson. And as a result, there is a natural square root of this virtual canonical bundle, which is just given by, so there is a natural choice of orientation data. Oh, sorry. Sorry, I think I need 10 seconds to charge the pen. So there will be like a natural square root of this virtual canonical bundle, which is given by the determinant of push forward of F due. Sorry, for some reason the pen doesn't work. Okay. Yeah. Yeah. Sorry for the inconvenience. So here we can choose. So I have the virtual canonical bundle. Isomorphic to the determinant determinant of pi push forward appeared, and then the choice of orientation data is given by the determinant of push forward f due. Okay, so then with the theorem is that using the D-critical local structure constructed above, together with the orientation data, the canonical orientation data choice here, then we can recover the computation of the absolute Motivic class for Hilbert NX. Defined in Baron, Bryan, and Sandroy's work. And right, so yeah, maybe I should write down the formula here. So the formula given by PBS 13 is that the generating series, this is given by this is when the surface is local P2, and then it's given by when the surface is given by Fn. Okay, yeah. So that's like the formula. So using the so this like gives the computation of the Motivic DT invariant using Joyce's definition is consistent with the previous computation given by BBS using their definition. Okay, so that's the main result. I have 10 minutes left. Or
Can I ask a quick question while you're there? So there are denominators in the formula. Is there an integral result? Right, because you have this exponential function. So is there actually an integral statement?
So this exp is this is the operator like in you can whether I'm not sure whether that's like an integral result or not, but it's a way to write down the exponentials in a neat way. So this is the operator given by which takes a power series. Sorry. So this is the operator like this. Did I answer the question?
Maybe.
Okay.
No, thanks.
Sure. Yeah. Okay. So so let me just say a little bit of the proof, maybe. Right. So the whole idea is based on the fact that Hilbert NC3. So this can be presented as a degeneracy locus. This is in BBS. So the idea is that if you think about the zero dimensional, yes.
But before we move away from Mark's question, I had interpreted it as thinking that the exponential of x is the sum of x to the n over n factorial, and that had actually kind of made some sense to me. Hey, we had to invert n factorial, and then Mark's question would be: would there be a way to get out of inverting n factorial. And then when you wrote this very cool looking definition of the exponential, you have in the exponent an element of k naught of varieties. And that's actually more confusing to me because the k naught of varieties, it's this abelian group and you can add things. The question isn't clear? I guess I'm curious about how you take, is the class of AN in these brackets an element of the K theory of variety of the Grothendieck group of varieties?
Yes.
So could you say something more about the meaning of raising 1 minus t to the n to an element of the Grothendieck group of varieties?
I guess this is like right. I don't have like a immediate answer at this point, I think, but maybe I can.
I'll think about it. I've seen.
I'll think about it and maybe like let you know maybe later. Sorry about that. Yeah, because this formula is like from like so after you show that the definition agree, then this formula actually coming from BBS papers like definition, and then you plug in the terms for the different target space. So yeah, so I guess I don't have a immediate answer to have a good explanation of that exponential term, but maybe I will let you know later. Yeah, sorry about that.
Thank you.
Sure. Yeah. So yeah, let me say right. Let me say a little bit about this proof. So we can following like the observation in BBS, we can present the Hilbert C3 as a globally as a degenerate locus, because the like a length n subscheme is consists of if you think about it, it consists of the information of n-dimensional vector space, which is the global section of OZ. And then there are 3 linear transformations from Vn to Vn. This corresponds to the action of x, y, z, the coordinate acting on the global section of the subscheme. And also the vector v in Vn, which is cyclic, meaning that the c, x, y, z, v will generate the whole Vn. So this V like plays the role of the 1 in the global section of this subscheme, right? And then then one can consider the space of whole Vn to Vn cubed cross Vn, and then this space naturally have a GLN action induced by the GLN action on Vn. So then there is a linearization of the trivial line bundle given by taking the determinant of GLN. And then so this gives a linearization of the trivial bundle. And then so let U be the stable locus. Okay. And then we can take the JIT quotient of this space cross Vn mod out by the GLN action, which is the U mod by GLN. So this space is like very close to Hilbert scheme, except for that we didn't require the 3 linear transformations pairwise commute, because the XYZ should pairwise commute. So then that's is like obtained by taking a local function on this space. So this we denote this by the non-commutative Hilbert scheme as the construction suggested. And there is a potential from the non-commutative Hilbert scheme to C. This is defined by the trees of X, Y, Z. Sorry. And one can easily check that dw equals to 0 exactly correspond to X, Y, Z pairwise commute. Okay, right. And then so this is exactly the locus of Hilbert and C3. So the idea is that the Hilbert and C3, so this is a very explicit construction of the critical local structure, because you already know that Hilbert and C3 can be globally realized as a degenerate locus. Then to give the critical local structure on Hilbert and X. So the strategy is that one first to find a cover of X, which this is the local Calabi-Yau threefold, consists of C3s. This may be note this by VI, this covered by VI, so that the Hilbert and VI, this will cover Hilbert and X. And also we fix a Calabi-Yau three form on X, such that, so this form is to fix the coordinate. So we can fix the coordinate on C3 such that this form restricted to each VI is just dx wedge dy wedge dz. So this is because the choice of potential is have a freedom of scaling. So this fixed Calabi-Yau form is equivalent to the change of coordinate actually have the same normalized factor. So the scaling factor is the same. Right, so this is the fixed cover. And then we already know that the Hilbert and C3 can be globally realized as degenerate locus based on the observation in BBS paper. So we only need to check the local sections to agree on the intersections up to ideal squared. And this can be done because the toric variety have a lot of automorphisms. So we can use automorphisms of toric variety. To make the change of coordinates, so that we only need to reduce the comparison only to toric invariant C3s. And then the last step is just to compare the sections on toric invariant C3s, and then that's like explicit, and one can check it in completion and complete the ring, and then check it in completion, and then like pull back and get the compatibility. So so the last step is to check the compatibility on the torus invariant C3s, and then that gives the compatibility of the sections and shows that there is a decritical local structure there. I think I will stop here. Thank you very much.
Thank you very much. Let's thank Yoon.
Thank you.
Open up for further questions, so please feel free to unmute yourself or type in the chat. So these invariants that you even have formulas for, they're counting some objects with some sort of deformation condition. Can you say something about the objects that these quantities are counting and the deformation conditions they satisfy?
Yeah, I guess I still couldn't say better than last time, right? But I will try to like formalize that better, and then maybe I think I will let you know when I have a more satisfactory answer. But the idea is that it counts the thing like where the deformation class vanishes. So the intuition is that it counts the thing where the abstraction class vanishes. So it's the cycle should correspond to the locus where the abstraction class of that object vanishes. So it's the count the object which actually deforms.
And can you remind me the name of these objects?
You mean the objects in the moduli space, or they are like coherent, some G-figure stable coherent sheaves with some fixed topological invariant.
And they correspond to curves of some sort?
Oh yeah, they you can think about them. So for this case, for the special case for Calabi-Yau threefold, and for the G-figure stable objects with this particular like fixed chain character, and then the trivial determinant, then they are ideal sheaves of one-dimensional subschemes. So they are always correspond. So they can think about as a generalization of curves maybe. So it have reduced curve. It could have like non-reduced curve. Could have embedded points.
Counting curves on threefolds with some deformation condition, and the magical count is in the Grothendieck group of varieties.
Yeah. But in the Grothendieck group of variety, that's like a categorification of the numerical counting. That's like I don't know whether it's correct to say this, but that's like I feel like it's like motivated from the original deformation abstraction definition, but it's more like a different structure. Like it's not. It's related to the abstraction theory. For definitely it's related to the symmetric abstraction theory. But it's more like the categorified structure on the moduli space. Sorry, that's the best I can say now.
Here's a quick question. You
Sure,
have
sure.
a P here with the 1 minus Euler characteristic of Milnor fiber. This new P. So to what extent do these patching conditions give a patching condition on the sheaf of vanishing cycles?
Which patching condition are you referring to?
Well, the one that you described. The one you have these conditions on the local. So you locally write your scheme as the critical locus of function. And then you have compatibility conditions. It says things glue together nicely to give you a well-defined class in some K-naught of varieties. Okay, but maybe probably it's a finer invariant. But you also have, once you have these local critical things locally described as critical loci, you have locally sheaves of vanishing cycles. And that's essentially describing the Milnor fiber in some sense. So my question is, to what extent do these patching conditions give you patching conditions to give a globally defined sheaf of vanishing cycles on the moduli space?
Yeah, I think so. I think there's the work by Joyce and I forgot the name of other author. I think there's a further paper by Joyce and other co-authors define the global. So this is like a globally well-defined Motivic class, and there is also a version on global sheaf of vanishing cycles.
Oh, okay.
Right. So it's locally also locally on the local. On the local charts on the globe on the degeneracy locus. There's a sheaf of vanishing cycles, and then need the orientation data to fix the error, the fixing of error term.
And who did that?
It's by Joyce and I forgot the other author's name,
Okay,
but
remember to send me an email, so I won't.
Sure. I will send you the reference. Yeah.
Thanks very much.
Mhm.
If there are no further questions, let's thank Yoon again.
Thank you.